show by the principle of mathematical induction that for all n belonging to the set of natural numbers, the following is true. Let us begin. Now here, what we'll do, before beginning, we're going to consider a statement. We're going to suppose that Pn is a statement which is given by, now here we're going to define the statement P of n as 1 over 1 multiplied to 2, added to 1 over 2 multiplied to 3, added to 1 over 3 multiplied to 4. This goes all the way up to the last term given by 1 over n multiplied to n plus 1. So it's given here that the sum of these terms, sum is n over n plus 1. So we're considering that this is the statement represented by P of n. Now in order to show that the statement is true for all natural numbers, and that means regardless of the natural number we pick up, the statement is always true, we will first consider n equals to 1. So let's say for n equals to 1, that in that particular case, P of 1, so here P of 1 means we are considering n equals to 1, which means there will be only one single term. So we only have to be concerned with the first term. So here we have 1 over 1 times 2. Or what we can do, we can take the general term, which is the last term here, and replace n with 1. We are going to get the same result here. So 1 over 1 times 2, that will be equals to, now on the right hand side, we have n divided by n1 plus 1. Now 1 over 1 times 2, that's 1 half. And on the right hand side, we're getting 1 half as well. So that means the statement is true for n equals to 1. Or in other words, we can say this implies that P of 1 is true. Now since P of 1 is true, what we'll do, we're going to consider the mth term. So let's say, let P of m, we're saying that P of m be also true. So if P of m is also true, then we can say that P of m, then we have the expression 1 over 1 times 2, added to 1 over 2 times 3, added to 1 over 3 times 4. So this is going to continue all the way up to the last term given by 1 over n times n plus 1. So this is going to be, so in place of n, we're going to replace with m. So we have 1 over m times m plus 1. That will be equals to m over m plus 1. So we're saying that this, let this be true. If this is true, and using this, we will need to show that P of m plus 1, which is the term next to that of m, so P of m plus 1 is also true. In other words, we need to show that P of m plus 1, so that will be such that we have the first term 1 over 1 times 2, added to the second term 1 over 2 times 3, added to the third term 1 over 3 times 4. This is going to go all the way up to the last term of Pm, so that's 1 over m times m plus 1. But we are considering here m plus 1. So what we'll have to do, we'll have to replace this m with m plus 1 such that we have 1 over m plus 1 multiplied to m plus 2. And this is going to be equals to, we're going to replace the m with m plus 1. So in the numerator, we have m plus 1 divided by the denominator, m plus 1 plus 1. So we have m plus 2. Fine. Now this is what we need to show. Now how do we show that this statement is true? So here what we will do, we will start from the left hand side. Now on the left hand side, what we have here is 1 over 1 times 2, added to 1 over 2 times 3, going all the way up to the second last term, which is 1 over m times m plus 1. Fine. Now what we'll do, we are going to replace this entire expression with m over m plus 1. Now why we are doing this, let's write down the last term as well. We have 1 over m plus 1 multiplied to m plus 2. The reason why we're replacing this some of these terms with m over m plus 1, because that's already a true statement. We've considered P of m to be a true statement. The sum of these terms gives us m over m plus 1. Okay, now what we'll do, now we're going to combine m over m plus 1 with 1 over m plus 1 multiplied to m plus 2. Fine. So this is going to be equals to, now we have a common denominator of m plus 1 multiplied to m plus 2. Fine. So in the numerator, we have m multiplied to m plus 2, added to 1. Now, we have m squared plus 2m added to 1 in the numerator divided by, we have m plus 1 multiplied to m plus 2. Now what we can do, we can rewrite the numerator as m plus 1 whole square. We are here using the completing the square. We have m plus 1 whole squared divided by m plus 1 multiplied to m plus 2. So let's factor out 1 m plus 1 from the numerator and the denominator. That's going to leave us with m plus 1 divided by m plus 2. And this is exactly the expression on the right hand side. We can compare. So here we had to show the right hand side, which was m plus 1 over m plus 2. So this means that since we have shown the left hand side, since left hand side equals to the right hand side, so here we have successfully showed that the statement p of m plus 1 is true. Now if the statement p of m plus 1 is true, hence we can say that the statement p of n such that we have the first term given by 1 over 1 times 2 added to 1 over 2 times 3 going all the way up to 1 over n times n plus 1 equals to n over n plus 1 is true. So this particular statement is true for all values of n belonging to the set of natural numbers. In other words, any natural number that we pick up, this is always going to be a true statement, which we prove using the principle of mathematical induction.